So thanks all for coming this morning, and let me just get started here by pointing out the elements of a tandem mass spectrometry experiment, which is going to be something that you're going to hear much more about in the next few days. What I'm going to try to do here in the time that I have with you is I'm going to describe how the major mass analyzers work, and I'm going to try to describe why they're used, provide some context with respect to the advantages and disadvantages. So why, for example, would we use a sector instrument as opposed to an ion trap or something like that? And hopefully at the end of this, you'll get a better idea of how these different analyzers fit into the grand scheme of things. But before I do that, and since this is a mass spec course, I want to talk about mass a little bit so that we're all using the same terms. And so what I've shown here on the right is an isotope distribution from insulin A chain that comes from a classic paper by Jurgi et al. That shows an isotope distribution. And so there's common terms that we use. And so the first is the nominal mass. And the nominal mass is just the integer mass value. For an atom, it's the most abundant isotope. For a molecule, it's the sum of all the integer masses of the atoms. So, this is where, when you go to have a coffee with your friend and you're talking science and you say, well, what's the mass of benzene? You'll say, well, let's see, carbon's 12. There's 6 of those, 72, and hydrogen's 1, there's 6 of those, so 78, right? So that's the nominal mass. The monoisotopic mass is for an element is the exact mass of the most abundant isotope. And so that's shown here. For hydrogen, it's 1.00 and 7/8, etc. For a molecule, it's the exact mass of the most abundant isotope of each element multiplied by that element, right? So that's the monoisotopic mass, most abundant isotope. The average mass is, well, in the case of an element, it's the atomic weight. So this is an abundance weighted average of all the isotopes. And for a molecule, it's the sum of all the atomic weights of the constituent elements. So that's the average mass. The most abundant mass, well, for an element, this would be the monoisotopic mass. But for a distribution of large molecules, it's greater than the monoisotopic mass. And so you can see here for insulin A chain, which is 3,000 some Daltons, the nominal mass is down here. There is no signal there. Here's the monoisotopic mass. The most abundant mass is the most abundant isotope. The average mass, as you see here, there is no signal for the average mass. It just happens to be the mathematical average. And then finally, a term that you'll hear a lot with accurate mass measurements is the exact mass, and that's the calculated mass that's based on some empirical formula. So some of these terms you'll see and hear later, presumably in this course. Okay, so how do isotopic distributions change with mass? And so it turns out that the monoisotopic mass for most molecules, peptides, for example, it will be the dominant or the most abundant signal up till about 1100 Daltons. And then once you get beyond that, then it's no longer the most abundant. And when you get up to about 7,000, the monoisotopic peak is almost not there. It's vanishingly small. As the mass gets greater and greater, the distribution becomes more or less symmetric, starts to look more Gaussian. And the width of that distribution grows sublinearly with mass. So there, I've given an example here. The full width half max of the isotope distribution at for about 3 kilodaltons is about 1100, whereas for 10,000 Daltons is about 2000. So it doesn't, that's tripling the mass, but the width of the isotope distribution is not a factor of 3 greater. But the most abundant isotope is always is somewhere between 0 and 1 Dalton, less than the average mass. And finally, for anything but the monoisotopic peak, you have the strong possibility for isotopic fine structure. And so what that means is if you have, for example, what we call the carbon-13 peak, there may actually be a nitrogen-15 there instead of a carbon-13. Or for example, the peak that's 2 mass units higher than the monoisotopic, we might consider to be mostly 2 carbon-13s, but that could also be 1 oxygen-18 and all carbon-12s. And those different combinations of isotopes have slightly different masses. And that's shown here in this expanded single mass peak showing the various the isotopic fine structure. And it turns out some mass analyzers have the resolution that's high enough that we can actually see this. Okay, so most of you are chemists. You'll hear, I'm not going to go through this in any kind of detail, but there are some terms here that you'll run into in the mass spec literature. You all know what isotopes are. You all know what isomers are, and there are various types of isomers, constitutional, stereo, and so forth. Then here's a term, isotopolog. So that's the same molecule, but different isotopes. And I give an example here, CH4, carbon-12, and hydrogen versus CH3D, where now we swapped out one of the hydrogens for a deuterium. Or another example would be a carbon-13 H4, that would be an isotopolog. You'll also see the term isotopomer, and isotopomer is a type of isomer. It's the constitutional isomer, and it's the same atoms, same structure, just different isotopic positions. And so that's another example of an isotopomer shown up here in this schematic. So as a mnemonic, you might know an isotopomer is an isomer, so it ends with the mer. And then here's an important one, isobars. And if you're a meteorologist, you're thinking, lines of constant pressure. But in mass spec, these are species that have the same nominal mass, but they have different elemental compositions, so they have different exact masses. And if you have an apparatus with high enough resolution, you can separate isobars. But isomers, of course, is a different story. And then finally, here's this definition of isotopic fine structure. And it turns out, using the terminology I've used here, the isotopic fine structure is populated by isobaric isotopologs. Okay, so I'll show you an example of an isotopic fine structure here later this morning. Okay, so now let's talk about the mass spectrum. And what I've shown here is a mass spectrum. It doesn't matter what it is. I pulled this off of my computer. It's a spectrum that was collected back in the 90s, I think. But it shows on the x-axis an M/Z scale, and on the y-axis it shows something that's related to signal level. It could be relative, it could be absolute. And for analytical chemists, there's basically two fundamental questions that people tend to ask. They'll ask, what is it? And then they'll ask how much. And it turns out that the x-axis in a mass spectrum is primarily giving information about what some substance is. That's the qualitative analysis part. So that's the mass scale here. And then the abundance scale is where we get our quantitative information. All right, so what is it typically we get from the x-axis? How much we typically get from the y-axis. And so when we talk about mass analyzers, we talk about what their relative strengths are for performance on each of these axes. So here on the x-axis, you have mass resolution, how well we can separate the peaks. Then there's mass measurement accuracy, how well we can assign the mass to charge value of that measured peak. And then the mass range is fairly obvious, is what's the range of mass to charge ratios over which our mass analyzer can separate the ions. So I'm going to talk about each of these in turn. For the y-axis, you'll have to tilt your head a little bit. There's how well you can measure the abundance, how repeatably, that's the precision, and how accurately. Then there's something called abundance sensitivity, which I will define here in a minute. And then dynamic range is any kind of analytical technique has a dynamic range. That's the range over which the signal level is linear with the quantity or concentration. Okay, so all the mass analyzers that I'm going to talk about have their own set of figures of merit in terms of these parameters I've just mentioned. So let's go through each of these quickly. So for the mass scale factors, resolution, and so I've copied out of this IUPAC document that defines terms in mass spectrometry, where they've defined mass resolution. And we can look at it down here. It's technically it's mass to charge over some uncertainty in mass to charge. Typically, you'll see it as m over delta m. And you have to define how you're determining delta m. And the most common way for people to do that is to measure the full width of the peak at half maximum, right? That's FWHM, full width half max. And so if you have any peak in the mass spectrum, you can take a look at that. You can measure its width in mass units at half max and divide that into the mass of the peak, and that will give you a feel for what the resolution is. I want to point out, though, that there are other definitions, other ways of defining this delta M in mass spec, and there's two common ways. One is the so-called 10% valley definition, and that's the delta M over Z at which two equally abundant peaks show a 10% overlap, and so that's shown here. That turns out to be equivalent to a 5% peak height definition for delta M. And both of them, for a Gaussian peak, those delta M values are about a factor of 2 greater than the delta M at full width half max. So as I tell my students, whenever you're writing or just talking about resolution, it really is important that you tell people the definition that you're using. And as I say, most often these days, people will use the full width half max definition. But just keep in mind, if you're using the 10% valley definition, that delta M is about a factor of 2 larger than it is at full width half max. So it's going to be roughly half the resolution as it is when you measure delta M at full width half max. So that's resolution. Mass measurement accuracy is how accurately we assign the mass of the peak. And so that's defined as the measured mass to charge ratio minus the exact mass divided by the exact mass. And that's a ratio, and it's normally expressed in terms of parts per million. And then the mass measurement precision. So anybody that's taken an analytical chemistry course knows the difference between accuracy and precision. And so here's some examples here pulled from a nice paper by Gareth Brenton. Here's a case where we have an accurate and a precise measurement. So all the measurements are tightly clustered, and the mean is right on top of the correct mass. Here's a case where the mean is also right on top of the correct mass, but there's a lot of scatter in the data, so that would be accurate, but not very precise. And then here's a case where you've got a bad calibration or something. You're getting you're getting good precision, but they're clustered on an incorrect mass. So that's inaccurate but precise. And then here's the disaster where you've got a lot of scatter in the measurements and the mean is also off. Okay, so that's the mass measurement precision. Finally, the mass range. This is the range over which an analyzer can register or can measure masses. Typically, people just mention only the upper mass to charge. They sort of assume that you can get down to 0, but that's not true in most cases, actually. So really explicitly, you should say what the real range is. It's often something like 50 to 2000 or might be 20 to 2000, or it could be 50 to 20,000. But anyway, that's the mass range. Okay, so now let's look at the y-axis, and linear dynamic range is something that all analytical chemists know what that is for any kind of a technique. That's the range over which the signal is linear with the analyte quantity or concentration. In a mass spec experiment, this is sometimes limited by the analyzer. As often as not, maybe even more often, it's limited by the ionization method. Could be limited by the detector. In any case, I'm just pointing out there that there is a possibility that your dynamic range could be limited by the analyzer. And we find with ion trapping instruments, they have limited ion storage capacity. And so in those cases, the linear dynamic range might be limited by the analyzer. Okay, abundance sensitivity, which is related to the dynamic range of the analyzer, is this ratio of the intensity of a large peak divided by the intensity of the background 1 mass unit away. And this turns out to be very important in isotope ratio measurements. So if you're trying to get a really accurate and precise measurement of the ratio of isotopes, you can't have the large peak, the tail of the large peak, interfering with the measurement of the abundance of the smaller peak. And just to show an example here, this is a really magnified mass scale for some uranium isotopes. And this is uranium-236, which is not a very abundant isotope in nature. It may be 1 part in 10 to the 7. It depends on whether the uranium's been through a reactor or been enriched and so forth. This is the uranium-235, which is the radioactive isotope of uranium. And then over here, and you can't see it because it's off the scale, way off scale is uranium-238. And you see that the tail of uranium-238 is now stretching in here over the range of uranium-237. And so basically, that's defining what the abundance sensitivity is. In this case, it's going to be typically you'll see it either in terms of ppm or the inverse. So this would be an abundance sensitivity of about 500,000 or so, which is actually very good relative to a lot of the instruments that most people use. And then, of course, abundance precision is the reproducibility with which you can measure that intensity ratio or that abundance ratio.
Hey, Scott, if I could jump in, somebody had a very, I think, pertinent question to this.
Okay.
So Dean Gerois asked, how is abundance sensitivity different from signal to noise?
Well, it's noise can come from anywhere. In abundance sensitivity, it's the tail of the more abundant peak that's stretching into the to the next mass down. So noise can come from anywhere, right? So that's almost like a separate issue that you have to deal with to make sure there's no chemical noise, for example, in your system, which could definitely limit the quality of an isotope ratio measurement. But you see here, you know, in between, say, the uranium isotopes 235 and 234, there's not very much chemical noise, and the tails of these peaks are not stretching into each other very much. So the difference here is in the abundance sensitivity measurement. The background is from the tail of a large peak. In signal to noise, the noise can come from anywhere. Is that, I hope that's clear.
Yeah, I think that answered the question.
Okay. All right, so let's got to keep moving here. And so, you know, I talked here about the figures of merit for the x-axis, figures of merit for the y-axis, and there's some others that are important considerations in the selection of a mass analyzer. One is the efficiency. So, you know, it may be the transmission and times the duty cycle. So, for example, a scanning instrument is only on one peak at a time. And so if it's a continuous ionization source, all the other ions are basically being thrown away. So that's not very efficient. If you have, for example, a pulse source and time of flight, and you collect all the ions off of that pulse, that's a really high duty cycle, and that's a better efficiency. So that's one thing to consider. If you're trying to follow fairly rapidly changing events, so oftentimes people will talk about, well, can you do this on the chromatographic timescale? You want to be able to generate enough peaks to get to data points across a peak to define the peak. So the speed can be important. And we'll see that the analyzers that we use, some are fairly fast, some are pretty slow. Compatibility with analyzers is a little bit, ionizers is a little bit less of an issue these days because people have figured out ways to make couple most any ionization method with any analyzer. And then there's the very practical kinds of things like the cost, size, weight, utility requirements. Is this a fieldable measurement? Is it a benchtop measurement? Is it something I need a big lab for? And finally, I put down here form of detection. So some techniques that we use electron multipliers or Faraday cups, or they may use an image current measurement. Image current measurements typically take tens of or more of charges. That's their detection limit. Whereas with multipliers, we can detect a single ion. So sometimes the detection limit can be impacted by the form of detection. Okay, so the last thing before I dive into analyzers, I want to make a really important point here. And that is, if your interest is in elements, the approaches that we use in mass spec are quite distinct from those where if your interests are in molecules. And hopefully from this presentation, you'll understand why that is. So we have very distinct approaches and technologies used in elemental mass spec versus polyatomic mass spec. And it turns out that if you're a real expert in elemental mass spec, you probably aren't an expert in molecular mass spec and vice versa, because the technologies that people use are so different that you know, you probably won't have a lot of experience in both. And so in the case of mass analysis, people typically use sectors. And that's really important for isotope ratio measurements, to a lesser extent the mass filter. And that's because in elemental mass spec, we typically know what we're looking for. We know what atoms we're interested in. There's not that much diversity. You look at the periodic table and, you know, there's a couple hundred elements. There's not millions and millions of them like there are molecules. So in most of those measurements, the questions that are asked are really focused on ratios typically. And so the premium is placed on the y-axis figures of merit. And sectors are really strong in those y-axis figures of merit. Whereas in the case of complex mixtures, proteomics, lipidomics, metabolomics, where you're looking at really complicated mixtures, that qualitative axis is really important. And so the premium is placed on the x-axis, so resolution, mass measurement accuracy, things like that. And so that calls for different choices when it comes to how you're going to do the mass analysis. Okay, so let's first then start with sectors. We don't use them very much in polyatomic mass spec anymore, although for many decades that was the gold standard. The sectors are still the gold standard in the isotope ratio elemental mass spec world. So I'm going to start here. Here on the far left is something that's called the right-hand rule. And so it applies to positive ions. If your fingers are pointing in the direction of the magnetic field lines and your thumb is pointing in the direction of the velocity or of the ions that are moving through the magnetic field, the force is normal to the direction of motion. It's shown here that the force is in the direction of the palm of your hand. And so I've shown a little cartoon of a magnetic sector here, and in this case, you'll have to, if you wanted to use the right-hand rule, you'd have to have your fingers face yourself, the thumb to the right, and then you would see that the force is in fact downward, and you see that the ions are going to execute a circular motion in the magnetic field. The force on the ion is given by the Lorentz equation, which is shown here. Right, so it's related to the velocity of the ion, the charge of the ion, and the cross B means that it's normal and related to the magnetic field strength. And if you accelerate all the ions out of the ion source with the same voltage, then they'll have a kinetic energy 1/2 mv squared. And if we solve for velocity and substitute that into these equations, we can do a little bit of algebra, and we find that the mass to charge ratio is related to the square of the magnetic field strength, the radius of curvature of the circular orbit, and the accelerating voltage. And so you can collect a mass spectrum with a sector magnetic field of fixed radius and fixed accelerating voltage by scanning the magnet, or you can fix the magnet and scan the accelerating voltage. Now you'll get a mass spectrum. Okay, so that's really simple, but it turns out that issuing from the ions, I want to point out here that you'll see here that velocity is an important term here. And so if all the ions don't have exactly the same velocity, then that's going to give rise to some spread in terms of the mass to charge that you measure. And it turns out that you'll get a velocity distribution coming from any kind of ion source. There's also a direction distribution. And the very first forms of mass spec were very first measurements were made by Wilhelm Wien and J.J. Thomson. And I won't show you any of their data, but the resolution in their instruments was horrible, and partly because they didn't have great vacuum, but also because they didn't correct for either the velocity distribution or the direction distribution. And so it turns out that the first major innovations in terms of improving the quality of a mass spec measurement was made in two different directions. One was made by Francis Aston, who won the Nobel Prize for his measurement of isotopes. He was J.J. Thomson's graduate student, and he understood the problems with Thomson's instrument. And so what he did is he used an electric field to deflect ions in one direction, and then he used a subsequent magnetic field to deflect the ions back in the opposite direction. And what he understood was electric fields will deflect on the basis of kinetic energy to charge. So that's 1/2 mv squared. So he knew if he matched the velocity dispersion by the electric sector with an equal and opposite velocity dispersion of the magnet, somewhere downstream there would come a focus. So in this case, if you look here, the lower velocity ions are deflected more because they have less kinetic energy, but they spend more time in the magnetic field, so they get deflected more back in the other direction, and at some point downstream there's a focus. And it turns out for different mass to charge ratio ions, they're focused at different points along this plane. And so he went from a resolution in Thomson's instrument of about 10, which was the state of the art at the beginning, to a resolution of several hundred. And then the other approach was across the pond in the United States. Arthur Dempster recognized that, in a uniform magnetic field, ions will execute a circular motion. And if they're issuing from the slit at different angles, they'll always come back to the same place, but you can't put a source and a detector right exactly at the same place. But he did see that there was a first order direction focusing at 180 degrees. So if he put his entrance slit here and his exit slit here, he would get a first order direction focusing. And so he built that apparatus at the University of Chicago, and his resolution was also several hundred, comparable to the resolution of Francis Aston. So those are two different ways. Those are ways to deal with each of those problems. And it turns out that with some time later, the principle of double focusing was introduced, where there was simultaneous direction and velocity focusing. And there's two classic geometries for that. There's a point-to-point geometry that's called the Near-Johnson geometry. And then there's a point-to-plane that's called the Maddox-Herzog geometry. And that's what gave rise to high resolution mass spec, because then the resolution could get up in excess of 10,000. Okay, I'm gonna move faster. So these are the sector figures of merit. What I want to point out, so the resolution can be in hundreds to 1,000 if it's single focusing, up to 100,000 if it's double focusing. Good mass measurement accuracy, single digit parts per million, because you can get nice stable magnetic fields, nice stable electric fields. The mass range could be as high as 10,000. You have to do some tricks to get that high. But this is the real strength here. Linear dynamic range of 10 to the 9. I don't have the time to explain why it can get so high, but you'll just have to take my word for that. Abundant sensitivity can also get as high as 10 to the 9. So just think about that. You can measure an isotope that's 9 orders of magnitude larger than the next isotope over. And then the abundance precision is also very good. So these three numbers are really, really good. And that's why their sectors are used in isotope ratio measurements. The rest of these, not so good. And so that they've sort of lost favor in the polyatomic world. So then the rest of them, time of flight, trapping instruments, and so forth, are the most important for polyatomics. So first, let's start with time of flight. It's probably the simplest conceptual form of mass spec. If you take an ion that's initially at rest and accelerate it through a potential V, it will acquire a kinetic energy of the number of charges times the voltage. And if we take that kinetic energy that they obtained, 1/2 mv squared, and solve for velocity, you see here that the velocity is inversely related to the square root of the mass. And directly related to the square root of the accelerating velocity. If we have some fixed traveling distance, you see here that the ions will travel a certain, will have a drift time that's divided by the distance divided by the velocity, or is the distance, drift distance divided by the velocity. And so we can rearrange that to give a mass to charge is related to the accelerating voltage, the square of the drift time divided by the drift distance. And so that's time of flight, and it works great if all the ions fall through the same voltage and there's no initial velocity distribution or direction distribution or position distribution. And so I can tell you from experience, it's really easy to build a time of flight mass spectrometer that doesn't work very well, but it's not so easy to build a time of flight instrument that works really well, because you've got some issues that you have to deal with. So I just point out here that the resolution, or this delta M that you get from a mass measurement using time of flight, is related to twice the uncertainty in the drift time. So you want to try to get that delta T as small as possible to get the good resolution. And so one way to do that is to make that the relative velocity small, and we do that by using high accelerating voltages. So the higher the accelerating voltage that you can use with your time of flight, if you have an initial velocity distribution, the lower the relative velocity spread will be by accelerating. So that's one thing that everybody does in time of flight, is we accelerate the ions by several thousand volts. Okay, so what are the contributions to this uncertainty in time? Well, if you're using a continuous source, it's how long one of the factors is how long you let the ions in. That's the gate time. And then, of course, there could be a velocity spread, which I'm trying to show here. There could be a direction spread. Some ions could even be going in the wrong direction. And then a position spread. And so how do we deal with those issues? The direction spread was something that in the early days using electron ionization was a problem. So you've got a gaseous source and some of the molecules are moving in the direction of the that you're going to pulse them. Some are moving in the opposite direction. You ionize them, they're given birth there at some particular point. And I just want to point out that here we have two different ions with the same initial velocity, one going in the right direction and one going in the wrong direction. And the one going in the wrong direction has to turn around and head back in the right direction. And when it does, it gets to this, when it reaches this point, it's got the same initial velocity, but it's always going to be behind the one that was moving in the right direction to begin with. And that gives rise to a fixed delta T or time spread, and in an absolute sense never goes away. And so the way to mitigate that problem is you have longer flight paths. And so the delta T is fixed, but if you increase the drift time by having a longer drift distance, then the relative spread gets smaller. So that's why we tend to like long flight tubes, long flight distances for time of flight. Okay, the velocity spread, there's a couple ways to do this. To deal with that. One is called time lag focusing, where you make the ions, but not in an accelerating field. You just make the ions, and the faster ions will move further downstream than the slower ions. Then you turn on your accelerating voltage, which is basically a voltage ramp, and the ions that are further along get accelerated less. The ions that aren't as far along get accelerated more. And so at some point downstream, there'll be a focal point. And that, if you put your detector there, then that will give you better resolution. But the problem with that time lag focusing is it's mass to charge dependent. So it's not a very general technique. A much better way to do things is to use an ion mirror, which was introduced by Mamren. And here what you do is you fire the ions into this mirror. The ions with greater kinetic energy will penetrate further into the mirror or up this voltage ramp. And then if you place the detector in the right place, the ions of the different kinetic energies will come to a focal point, which is illustrated here. If you have here's three different velocity vectors, and over time you see the faster ones moving further. The faster one penetrates further in the field that's shown here. It gets reflected back, and it's further behind because it traveled further. But if you have the detector in the right place, you can get all three ions with different velocities but same mass hit the detector at the same time. And so that's very, very commonly seen in modern time of flight instruments. How do we deal with the position spread? So here's an example here of, here's I've got ions in different positions when the accelerating voltage is turned on. So these ones that are here closer to the back, they roll down the hill farther, so they get accelerated more. The ones that are shown here, they don't get accelerated as much, so their velocities aren't as high. And so you'll see here, it turns out that, again, at some point, these have further to go, but they're moving faster than these guys. So at some point there will be a focus, but it turned, and there's a little bit of arithmetic here to show where that focus is going to be, but it turns out that that spatial focus is not very far from the source. So the drift length is pretty short, so it doesn't lend itself to very good time of flight. So that doesn't work very well. But you do notice now what you have is your position spread is no longer there, but now you have a velocity spread. So you've converted your position spread at this point to a velocity spread at this point. And now if you use this as one of your focal points for your reflectron time of flight, then you can correct for that position spread by using, again, a reflectron. And I'm going to skip this slide and show this is, again, the reflectron. And if you use the focal point here, so this is this spatial focus. Here's as a function of time. This is distance. If you have your the focal point, one of the focal points for your reflectron be this intermediate spatial focus, then you can bring all the ions to a focus here at the detector. If they start off in different positions, it gets converted to a velocity distribution here, and you can correct that with a reflectron. Okay, if you have both at the same time a position spread and a velocity spread, now you're in trouble. So it's really difficult to correct for them both at the same time. So what we see in modern time of flight instruments is people work really hard to make either the position or velocity spread small, and then they use a reflectron to correct for the other distribution. And so in the case of a continuous source, we use orthogonal acceleration to do some of these things. So the idea here is we take a beam of ions that's coming from a continuous source, might come from a trap or something, and we send it into this region, and they're all moving in a nice collimated group of ions, and then we pulse them into the time of flight. They go through a reflectron, and then we detect them. So this solves a lot of problems. It's a big innovation in time of flight because it decouples the gate time from how many ions that you actually have in your pulse out region. So these ions are coming in fairly slowly, and once this region is filled, you can dump the ions into the flight path. You've accelerated them to some high velocity. They go through that and hit the detector while you're refilling this region. And if you have the fill time comparable to the flight time, then you can get pretty efficient coupling of this continuous ion source with time of flight. So that was a really important innovation. And so you'll see lots of that these days. You know, I'm just showing a commercial instrument that's got 2 reflectrons in it. So here's this W-shaped time of flight. They're trying to get a long drift distance, and they've got a couple reflectrons here to bounce the ions back and forth and correct for the position distribution. So in this case, there's a very little velocity distribution normal to the direction of the ions, and mostly what you have is a position distribution. And the reflectron will correct for that. So here in modern time of flight, you have 2 types of situations. You have a pulse source from a surface, that would be MALDI, and you have continuous ionization, that would be any ambient ionization technique, electrospray, for example. So in case 1, you've got a pulse source, the ions are coming from a planar surface. There's no turnaround problem. There's minimal position spread because they're all coming off of the same point on the surface. And so all you really have is a velocity spread. And so you deal with that with a reflectron. In the case of a continuous source, you inject ions into a field-free region, normal to the direction of ion extraction, very narrow velocity distribution in the direction of ion extraction, a larger distribution in position, which you can correct for with the ion mirror. So time of flight, you know, in the 60s, the detection electronics weren't so fast, poor duty cycle with continuous sources, but with pulsed ionization and orthogonal acceleration, time of flight's had a resurgence. You can get resolution as high as 60,000 in commercial instruments. Mass measurement accuracy can be very good. Single-digit parts per million is very common. The mass range in principle is unlimited in time of flight, but it is effectively limited by the detection technology. But I've seen well in excess of 100,000. Linear dynamic range is okay. It doesn't compare with the sector. Abundance sensitivity also doesn't compare with the sector, and neither does the abundance precision. But these three factors are quite strong. And also the efficiency can be good. The speed, it's the fastest form of mass spec, so it is directly amenable to separations. Moderate price, can be benchtop or larger, and the detection is with a multiplier or a channel plate. Okay, now we're going to move on to a very different technology, and that's Fourier transform ion cyclotron resonance. Again, we go back to this is the Larmor equation. The force is related to the charge times the velocity multiplied by the magnetic field, or normal to the magnetic field. Again, that's equal to the centripetal energy. If we recognize that the angular velocity is the linear velocity divided by the radius of the circular orbit in the magnetic field, we'll define that as omega. We can plug that into these equations, and you come out with the basic relationship between cyclotron frequency and mass to charge. And you see that the cyclotron frequency is linear related to the magnetic field strength and inversely related to the mass to charge ratio. So if you can find some way to measure that frequency, then you can get out the mass. And the way that's done is by taking a population of ions and accelerating them coherently to the point where they're oscillating around in a cell where you can detect the ions. The image of the ions as they go past each of these plates, it's a differential kind of a signal. And if you take that image current measurement, this is what it might look like in the time domain. You convert that to the frequency domain via fast Fourier transform. And using that equation I just showed you, you can convert frequency to mass. So that's how you get out the mass spectrum. And it turns out that if the longer you make the observation and the higher the cyclotron frequency, the better the resolution. And so I've just shown here some examples here. 150 millisecond measurement of the time domain signal gives you a resolution that looks something like this. Whereas if you listen for 1.2 seconds, you'll get much better resolution, and you can see that these isotopes here, this isotopic resolution is much better longer the time. So in ICR, we want the magnitude and the stability of the ion frequency to be really good, really high, and the magnitude of the observation time to be very long to get really good resolution. So there's in order to get that T observation to be long, you have to be able to trap the ions for a long time, or you have to be able to observe the ions for a long time, so you have to trap them. So the way to trap them is you put some voltage on some trapping plates, or these orange plates here, and so that the ions can go back and forth in this dimension while they're undergoing their cyclotron motion here in X and Y. And so we have our detection plates where we can listen to the ions. We have our excitation plates where we can excite them to larger orbits so that we can detect them. And then in this direction, you have the trapping. But that gives rise to two different kinds of motion, the trapping motion back and forth, and also what's called the magnetron motion. And trapping motion looks like this. They're going back and forth in this electric field, and it is also mass to charge dependent. And once we get to the orbit trap, we'll see that this is actually the motion that the orbit trap uses to measure mass to charge in its trapping motion. But the problem motion is the magnetron motion. So once you put some DC potential on these two trapping plates, it actually is pushing ions out in X and Y. And so that's what's shown here. What the electric field looks like in the XY plane is the ions that are in the center of the trap undergoing their cyclotron motion are really at the top of a potential hill. And they really would like to move down that hill. And that can happen because collisions will convert cyclotron motion to this rotation around the top of that hill that's called magnetron motion. So this is cyclotron motion here, where the ions are undergoing some small amplitude oscillation around here. And then they undergo a collision and the cyclotron motion gets converted to magnetron motion and they start falling down the hill. And more collisions and they'll eventually hit the walls of the cell. That's called radial diffusion. And when the ions are lost from the cell, you can't hear them anymore. And so that limits the transient length and therefore limits the resolution. So ICRs are always want to operate ICRs at very, very low pressure. Okay, and so, I'll just point that out here. In an ICR, the observed frequency is the cyclotron frequency minus the magnetron frequency, which is low, maybe about 100 hertz. And is also impacted by mutual repulsion of the ions or space charge. So you want to keep space charge down. You want to minimize the trapping voltage to minimize the magnetron motion, keep the pressure down, and that will allow you to listen for a long time to get a good resolution. And so I'll just show you once you've got the gas pressure low enough, what's the next limiting step? And it turns out it's basically how harmonic the potential is in the cell. I'm not going to go into all this. I'll just point out here's pioneering work by Eugene Nikolaev with a different kind of cell here that gives really harmonic motion in the trapping motion such that the ions always have this exactly the same frequency or very close to it everywhere they are in the cell. And so that allows you to get up to really high resolution with trapping times of tens of seconds to minutes, because you're not losing ions either due to collisions or to dephasing, which can happen if this field's not harmonic. So the ICR's figures of merit. It's the world record holder in resolution. I've seen tens of millions of resolution in ICRs with really long trapping times. Really, really good mass measurement accuracy, less than a ppm. If you're careful about calibration. Mass range is 10 to the 4, but remember the frequency is inversely related to mass. So the frequency decreases as 1 over the mass, and so the resolution is not nearly as high at high mass as it is at low mass. It's a trapping instrument, which means you have to deal with space charge problems. So the dynamic range and abundance sensitivity don't compare with a sector at all. And the abundance precision, typically you have to meter the number of ions in there, so that's not so great either. Speed is not very good in an ICR. If you're going to get high resolution, you have to listen a long time. So it's not a very fast form of mass spec. And the cost is quite high because you need a superconducting magnet. So it makes it a lab instrument, and its detection is by image current. But with ICR, everything gets better with magnetic field strength, which is why there's a 21 Tesla magnet down in Florida and one over into PNNL to get where the world record stuff happens. Okay, wouldn't it be great if we had the characteristics of an FTICR without a magnetic field? And this is something that was provided to us by Alexander Makarov when he introduced the so-called Orbitrap, which is an electrostatic form of Fourier transform mass spec. And so the way that this works is he's combined a orbital trapping around a central electrode where the ions are orbiting around the central electrode. And in the orthogonal direction, he has a harmonic quadrupolar field where the ions are going back and forth with simple harmonic motion. And he can effect that kind of motion using a geometry that looks like this, a spindle type inner electrode and this shaped outer electrode. And, you know, it didn't come from nothing. So there was something a long time ago called the Kingdon trap, which was a way to trap ions using a wire surrounded by a cylinder. And then sometime later, Knight tried to provide this harmonic sort of quadrupolar field to give ions oscillatory behavior like so. Wasn't perfect. And what Alexander did was showed how to create a more perfect field, and with modern machining was able to make that happen. So in order to make this work as an ICR though, or as an FTMS, you had to split this outer electrode into two pieces so that you could measure the image current as ions go back and forth.
Hey, Scott.
Yeah.
You think you'll be able to wrap up in a couple of minutes here for us?
Yeah. Okay. So I'm going to have to skip a lot, but anyway, the most important motion, there's three motions in an Orbitrap, just like there's three motions in an ICR or analogous to that. But the most important motion is the oscillatory motion that goes back and forth between these electrodes. And I can't get my pointer to settle down, but it's this oscillatory motion back and forth. And I'll skip that. The ions are injected off axis, so they come into the Orbitrap up here. And once they're injected off axis, they'll start undergoing harmonic motion back and forth like this. And it's this motion that's detected as an image current in the time domain and then sent for fast Fourier transformation to the frequency domain, which you can calibrate to mass. And so the Orbitrap has really good resolution, hundreds of thousands, really good mass measurement accuracy because you can make really nice stable electric fields. The mass range up these days, you can buy an Orbitrap that goes up to 80,000. Linear dynamic range, it's a trapping instrument, so it's not like as good as a sector. I don't really know what the abundance sensitivity is. I haven't seen anybody measure that. Probably somebody has. Abundance precision is can be good if you're careful. And then the speed is it's kind of slow because it's a FT experiment, but a lot less expensive than a big magnet. And it's mostly a lab instrument, could be made smaller, but it uses image current detection. And since I have to wrap up, I'm just going to comment here that the last part is electrodynamic mass analyzers. These are mass filters and ion traps. Conceptually, these are the most difficult forms of mass analysis to understand. So I sort of left this for last because I suspected I wouldn't be able to get to it. But basically, I mean, this was invented by Wolfgang Paul in the 50s. And I can't go through all the development part, but it's very logical steps in coming up with this approach. But if you have these four cylinders, or ideally they'd be hyperbole that are parallel here, and you apply simultaneously a sine wave and a DC potential, you can create DC and RF quadrupolar fields. And it turns out that if you go through the mathematics, you can put this in terms of a Matthew equation. The Matthew equation, the solutions to the Matthew equations apply to the motions of ions in traps and mass filters. And so to understand, you know, the trajectories of the ions in these devices, you can just use the Matthew equation. Summary of the Matthew equation is shown in a so-called, this is like a 2D map of the solutions of the Matthew equation. And where ions are simultaneously stable in all directions is where the ions will be able to transmit through the instrument. Anyway, it turns out that if you fire the ions through quadrupole, you have a a region of instability that's filtering out the high mass ions, a region of instability that's filtering the low mass ions, and you can apply operating conditions where, you know, the Goldilocks ions, not too high in mass, not too low, will transmit through the device, and that's why it's called a mass filter. So it doesn't perform as well, but it is under electronic control. It's a really great device for isolating ions, and people do use them as sort of low-end mass analyzers in LCMS and GCMS. Traps also work on the same principles. They just store the ions, and in this case, rather than transmitting them sequentially, which is called mass selective stability, we eject ions, we store them all at once, and then we throw them out in a mass-dependent fashion. That's called mass selective instability, which was invented by George Stafford. So I'll just skip to the figures of merit. For traps, the resolution, again, moderate, not great mass measurement accuracy. They can be extended up to quite high mass to charge range. Since it's a storing instrument, the linear dynamic range is not so good. Abundance sensitivity is not great, but they're awesome devices for being able to store ions and execute multiple stages of mass selection with reactions that take place in between them. So most of the high performance instruments these days will have a trap in them, but the readout is done by orbit trap or time of flight, something like that. Okay, so that's my wrap up of the mass analyzers, and I hope you know what the flavor that you got from this is that there's lots of ways of measuring mass to charge ratio, which is the best one for your application is determined by the figures of merit and the nature of the scientific question that you're asking. Okay, thank you.